Welcome to the 7th year of the Nutritionist webinars. I'm Marianne Fessenden, Educational and Academic Liaison for AMTS and your host for this series. This August 11th webinar is the 5th in our 2022 series focusing on emissions. Today's webinar features Dr. Joseph W. McFadden, an Associate Professor of Dairy Cattle Biology and Northeast Agribusiness and Feed Alliance Faculty Fellow in the Department of Animal Science at Cornell University. McFadden received a BS degree in animal science with distinction in research from Cornell University, an MS degree in animal science from the University of Illinois, and a PhD degree in dairy science from Virginia Tech. He also completed a postdoctoral fellowship in the Department of Neuroscience and the Center for Metabolism and Obesity Research at Johns Hopkins University. From 2012 to 2017, he served as an assistant professor in biology at West Virginia University. Since returning to Cornell faculty in 2017, McFadden has led a research program focusing on dairy cattle nutrition with a focus on improving nutrient digestibility, liver and gut function, and the efficiency of milk production. He is leading the development of a Cornell program and center to evaluate the effects of feed additives and drugs on methane and milk production using standardized procedures. He actively manages an investigative team of 25 individuals with support from NSF, USDA, FFAR, and over a dozen industry partners. Following is a recorded presentation and the question period from both the morning and afternoon webinars.
Hello, everyone. Thank you for joining this seminar today. My name is Joe McFadden. I am an associate professor of dairy cattle biology and nutrition at Cornell. Some of you may know that my research focuses on the efficiency of milk production and energy metabolism in the dairy cow. I definitely enjoy studying the complete system, and recently this has started to include methane production. Today it is my goal to describe various solutions to enhance animal performance and inhibit enteric methane, identify various critical gaps in knowledge that are needed to expedite the development of methane inhibiting technologies, and discuss the holistic approach that is required to define the efficacy of such feed additives. And I think there is some interest to know how Cornell hopes to contribute in this area, and I hope to share some of the recent developments we have been working on. I think we all can agree that there are climate change believers as well as skeptics in the world. Fortunately, we have direct climate data for over a century, and although climate and weather are uniquely defined, I often tell skeptics that since our climate has changed in the past, it is conceivable that it will change in the future. Indeed, the Intergovernmental Panel on Climate Change in 2021 said that it is virtually certain that irreversible committed change is already underway. That sounds pretty gloom and doom, but this is a projection based on numerous models that anticipate further increases in atmospheric carbon dioxide, methane, and nitrous oxide emissions by human activities. These changes are likely to cause global warming and modify precipitation patterns. The latest New York State Energy Research and Development Authority climate change report suggests about 7 millimeters more precipitation per decade and 3 times more severe heat events by the end of the century. I want to make a point and state that enhancing the adaptability and resilience of animal ag is simply smart and should remain the focus dependent or independent of the climate change narrative. The more approaches that we can provide farmers to enhance the energetic conversion of feed to meat or milk, enhance the heat tolerance of high-producing dairy breeds, improve nutrient digestibility and bioavailability, and improve animal health and the nutrient composition of animal source foods, the more adaptable and resilient animal ag will become. Although there is an active debate about the relative contribution of livestock production to greenhouse gas emissions and climate change, and we are aware that methane emissions from ruminants are part of a natural biogenic carbon cycle that involves plants and animals, livestock production emits methane and nitrous oxide. The concern is that 100-year global warming potential for methane and nitrous oxide are 23 times and 296 times the global warming potential of carbon dioxide, respectively. Reducing these emissions has potential to provide quick action to slow the progression of climate change. However, the release of fossil carbons has to be addressed in parallel. In ag, focus has been placed on ruminants. The Global Livestock Environmental Assessment Model, or GLEAM, states that the production of beef, meat, and cattle milk are two commodities with the highest total emissions, accounting for 3 and 1.6 gigatons of CO2 equivalents, respectively. But we should always consider emissions on the basis of nutrient supply for human consumption. By this practice, buffalo meat is the commodity with the highest emission intensity, with an average of 404 kilograms of CO2 equivalents per kilograms of protein. This is followed by beef meat, with an average of 295 kilograms of CO2 equivalents per kilogram of protein. Meat and milk from small ruminants, including goats, and milk from buffalo are close behind. Therefore, the focus on cattle or buffalo has merit when compared to other animal species used for food production. One thing that I have learned is that the solutions to methane mitigation are likely to be unique based on the region. Latin America and the Caribbean have the highest level of emissions, with 1.9 gigatons of CO2 equivalents caused by the production of beef. East and Southeast Asia have 1.6 gigatons, followed by South Asia with 1.5. North America and Western Europe show similar levels of emissions, around 0.6. And cattle and buffalo are the primary contributors in all of these regions. Specifically, within livestock agriculture, the methane produced by enteric fermentation due to digestion is the major contributor. This can be highly influenced by beef quality. Nobody's going to disagree with that. And there is also a lot of attention on manure, since it is a source of methane and nitrous oxide, whereas methane is released during anaerobic digestion and nitrous oxide is generated during manure ammonia decomposition. I will provide a couple examples today about feed additives that reduce methane, but also modify protein digestibility and nitrogen utilization in the cow. So we must also consider nitrous oxide emissions in parallel. As I am sure many of you know, the U.S. and other developed countries have led in the enhancement of milk production efficiency because of improvements in genetics, nutrition, and management. This is attributed to the dilution of maintenance energy requirements in high-producing cattle. The science states that maintenance energy requirements are fairly constant. Therefore, as an individual cow produces more milk, the percent of energy requirements that she uses to maintain vital life functions decreases. This benefits our environment because we require less land, water, fossil fuels, and cattle to produce an equivalent amount of milk. Feeding cows at their requirements using ration formulation software like AMTS ensures that we are meeting nutrient demands for lactation, but also ensuring that we avoid overnutrition and minimize the negative environmental impacts of animal ag. From a nutritional feeding perspective, the development and application of the total mix ration, use of energy-dense diets, enhanced fiber digestibility, lower forward to concentrate ratio diets, feeding adequate essential amino acids and energy from fat and non-fiber carbohydrates, and many other advancements are the reasons for improved efficiency. I think this is common knowledge, but if we want to immediately reduce greenhouse gas emissions globally, we must work to enhance the productive efficiency of ruminants in developing countries. One country of personal interest that needs immediate attention is India. It has 300 million bovine, that is 3 times the U.S., produces 22% of global milk production, and has 125 million smallholder farmers raising 2 to 5 buffalo or indigenous or crossbred cattle with an average milk production of just 5 liters per day. Across all Indian states and territories, mean greenhouse gas intensity per unit of milk for crossbred cows is 1.2 kilograms of CO2 equivalents per kilogram of milk versus 2.96 for indigenous cows. For perspective, the average enteric methane emissions intensity in the United States is 0.25 kilograms of CO2 equivalents per kilogram of milk. A similar situation is observed when we evaluate emissions on the basis of milk energy. In India or countries in similar scenarios, we must continue to identify ways to use AI to enhance genetics, enhance the supply of concentrates and high-quality fodder, but more importantly, define a feed composition as a means to support the development of ration formulation as a means to meet the requirements of bovine to reduce emission intensities. Historically, the study of milk production efficiency has centered on the energetic conversion of gross energy in feed to milk energy or tissue or maintenance energy, especially when studying nutrient partitioning. However, the study of energetics within the framework of methane inhibiting compounds has been poorly characterized. And the reason is the limited use of indirect calorimetry using respiration chambers. This approach enables the investigators to estimate heat production through the measurement of oxygen consumption, CO2 and methane emissions, and urinary nitrogen excretion. Determining methane and urinary energy also enables us to define metabolizable energy. In diets with 70% energy digestibility, energy losses as methane can range from 3 to 17% of digestible energy consumed. A moderate decrease in methane production, now let's just say for the sake of it, 25% or less, that may only increase metabolizable energy by 1 to 4%. Since the conversion of metabolizable energy to net energy is about 65%, it is likely very difficult to observe an increase in milk production with low to moderate methane inhibition. Therefore, a more robust inhibition of methane production in the rumen, let's say more than 50%, without compromised dry matter intake or digestibility, may be required to improve milk production. This is especially concerning when the current known options to reduce methane production by more than 50% is limited to a single feed additive that I'll talk about shortly. If you read pubs focused on methane inhibition, you'll often find a statement that says that methane energy accounts for 2 to 12% of gross energy intake. The figure on the right is the origin of that statement. It describes the observed relationship between digestible energy intake and methane production as a percentage of gross energy intake as measured using indirect calorimetry. The low and high for methane production is about 2 and 12% respectively. In general, as diet digestibility increases, variability in methane losses also increases. Johnson & Johnson attribute this variation to variations in carbohydrate fermentation and rate of passage and the ratio of acetate to propionate produced, considering that propionate production acts as a hydrogen sink. The authors also considered a hypothetical situation. For instance, if the acetate to propionate ratio was 0.5 to 1, the loss of substrate energy as methane would be 0%. In contrast, if acetate production occurred without propionate production, energy losses in methane would be 33%. So typical ratios of acetate to propionate, though, are 1 to 4, so variation is wide. So overall, we can't ignore the fact that enhanced milk production efficiency reduces greenhouse gas emissions per unit of intake or unit of milk or milk energy. This particular study evaluated data from 20 energy metabolism experiments involving 579 lactating dairy cows varying in genetic merit, lactation number, stage of lactation, and live weight. Methane energy as a proportion of energy intake, whether it be gross energy, digestible energy, or metabolizable energy, or as a proportion of milk production, can be reduced by increasing milk yield and energetic efficiency. This is something we all recognize, but something that is not achieved in developing countries, and also this is something that is not simply acknowledged very frequently by the consumer. And so there is room for improvement to fill those gaps. Now, methane yield for dairy cows has been predicted from the proportions of volatile fatty acids in their rumen fluid. Here's a clear relationship between acetate and propionate production and methane yield. You can still observe clear variability. In this particular case, the use of sulfur hexafluoride was used to measure methane 4 hours after feeding. This SF6 technique involves the use of SF6 dose into the reticular rumen and the subsequent collection of time-integrated breath samples with analysis of methane and SF6 concentrations. The calculation of daily methane emissions is based on the methane SF6 ratio concentrations adjusted for background concentrations and the specific permeation rate of SF6. SF6 does not measure total emissions, is not fully quantitative, and can be impacted by sampling time relative to feeding and duration of feeding. Other factors such as diversity of the microbiome or alternative fermentation pathways could explain the variability between the VFA levels and methane yield as observed here. Now, there is more than one study looking at forage concentrate content of diets and their effects on methane emissions. So it's a logical place to really start to focus on how dietary ingredients influence methanogenesis. Now, this study explored the effects of a 65-35 versus a 35-65 forage to concentrate ratio diet with or without 50 grams per kilogram of dry matter of sunflower oil. All right. The high concentrate diets are shown on the right-hand side with the H, and the low concentrate diets are shown with L, and the SO stands for sunflower oil. Although I will get into the effects of oil on methane production in a minute, feeding more concentrate, in this case rolled barley and ground wheat, doubled dietary starch content. It lowered rumen pH, increased total VFA production, increased propionate, shown here, when decreasing acetate, and decreased ruminal methane production per unit of energy-corrected milk or as a percent of gross energy intake. Again, this makes me think about India and other countries like it, where you have a situation where the country in today's scenario is unable to provide the concentrate required to meet the energetic demands of lactation. So changes in crop production and feed processing will need to adapt to enhance efficiency and reduce methane in developing countries. It also makes me think about trials that study methane inhibitors. A study that's performed in Europe versus a study that's performed in North America, knowing that the forage to concentrate ratio in the diet is likely to be higher in a European diet than a North American diet. And how is that methane inhibitor going to behave in those two different scenarios? And that is because, the forage concentrate ratio is going to influence fermentation, altering propionate supply. And so we need to think about how these dietary strategies and methane inhibitors are going to work within the context of the base diet that is going to conform to regional norms. Here's a simple study. I shouldn't call it a simple study, it's a simple design to explore the effects of replacing alfalfa silage with corn silage from 0 to 100% replacement. Forage concentrate ratio was 60-40. Corn grain and soybean meal were used as replacements to keep NDF and crude protein constant. Starch content increased with corn silage inclusion. That makes a lot of sense. Milk yields increased and milk fat content decreased as the inclusion of corn silage increased. Methane per unit of dry matter intake, or as a percentage of gross energy intake, shown here in the middle, decreased at 100% corn silage. They also decreased per unit of milk, or as a percentage of digestible energy. And dry matter, organic matter, and crude protein digestibility increased, but NDF digestibility decreased, shown at the bottom. The rumen pH was also lower, which likely inhibited the growth of cellulitic bacteria. And in support, the acetate to propionate ratio decreased with the inclusion of corn silage, which is not shown. That lower rumen pH is less favorable to methanogens and associated protozoa. And also not shown here is nitrogen in feces was also reduced, suggesting lower nitrous oxide emissions from manure. That said, that wasn't specifically measured here. I also found another paper when I was starting to think about this. It was a work from the Netherlands that was looking at the maturity of corn at harvest. And they were able to show that with increased maturity at harvest, that this reduces methane production when compared to gross energy intake. I recently had a chance to visit the Cornell lab at the University of Nebraska. This is just a few weeks ago. For those not familiar, they focus on the use of indirect calorimetry to better define energy utilization in Jersey cows. The objective for this study was to determine the impact of varying lignin concentrations across two diets similar in NDF content on energy and nitrogen utilization. The diets varied in corn silage, alfalfa hay, ground corn, and soybean and cottonseed hulls to create two diets that were comparable in crude protein and NDF, but had 9 versus 13% lignin on an NDF basis. Panel A shows marked decreases in dry matter, crude protein, NDF, starch, and energy digestibilities in cows fed the high lignin diet. You see that here. In panel B, milk energy was lower for high lignin diet, as was gross digestible and metabolizable energy. The efficiency of converting gross energy to digestible energy, shown at the very bottom of this table, was also lower. With regards to methane energy was not influenced, but methane production per unit of milk protein was increased in cows fed the high lignin diet. Not presented here, but describing this work, this was an abstract, as a percent of intake, nitrogen partitioning toward milk decreased, but increased toward feces in cows fed high lignin diets. So low lignin diet favorably lowered methane per unit of milk protein, but since methane yield did not change, this was due to the enhanced effect of a low lignin diet on crude protein digestibility, enhanced use of nitrogen for milk protein. Now, this is an important reason why we need to consider nitrogen utilization in studies that evaluate methane production. And I think it would have been very interesting to consider manure nitrous oxide emissions as a percent of nitrogen intake in this study. We had other conversations when I visited, and some of Dr. Kononof's other work as exploring the factors that impact the variance observed for methane emissions, and has concluded that we must consider the inherent animal difference in this energetic loss. For instance, we had a conversation about the role of the host genotype, and perhaps such data should be a prerequisite for collection in various chamber experiments. One area that I think needs far more research should be plant breeding efforts to enhance the presence of methane inhibiting compounds in the forage. I believe these efforts are going to clearly benefit developing nations. They're not going to have the feasibility of providing supplements, perhaps, in diets, and are going to rely more on forages. This said, there has been effort on obvious compounds in forages such as polyphenols, tannins, and saponins. Their efficacy is relatively low, and in vivo tests evaluating forage comparisons in a single study are needed. Here is the only in vitro study that I'm going to discuss today, but because I say this because I'm a firm believer that an in vitro approach has the sole purpose to initiate inhibitor discovery, with the realization that the in vivo outcomes most often don't completely or incompletely recapitulate what is observed in vitro. That said, this study examined the effects of various forage species, including cultivars within forage, on methane production from rumen fluid. They tested these forages in the absence or presence of PEG, or polyethylene glycol. You can see the top row here is the negative PEG, and the bottom row is plus PEG. While PEG is a tannin binding agent, and so they use this as a tool to determine whether the inhibitory effect of the forage on methane production was dependent upon tannins. Now, what they observed was there was almost a twofold difference in methane production between species of cultivars, and between species in cultivars. So just look at the first two, for example, chicory and sula. They're looking at, in the absence of PEG, there's about a twofold difference there in methane production. All right, now, they also were able to show that sula and big trefoil, two particular proanthocyanidin-rich forage species, had the highest methane reduction potential of up to 47% when comparing samples with and without PEG. And so you can see here, it's sort of hard to understand this figure first looking at it, but in the positive PEG, you can see that methane production was higher in the presence of PEG as compared to the absence, and that's denoted by the difference here in the subscripts A and B, the lowercase subscripts. And that's because PEG acts as a tannin binding agent. Now, the anaerobic reduction of nitrate is energetically more favorable than CO2 reduction. Therefore, the presence of nitrate in the rumen has potential to redirect hydrogen from methanogenesis to nitrate reduction. Various studies in sheep and cattle have observed reductions of approximately 10 to 30% in methane yields with dietary nitrate. Now, this study was in the Netherlands, explored the effects of dietary nitrate in place of urea on the basis of nitrogen supply, on the conversion of gross energy to milk energy based on the principle that nitrate can be reduced to nitrite and then ammonia. At 21 grams of nitrate per kilogram of dry matter, they observed a 16% decrease in methane production. You sort of see that there right about in this area. It's estimated that this reduction was only 59% of its theoretical potential. Therefore, nitrate was not fully reduced to ammonia. It was hypothesized that a portion of the nitrate, or nitrate for that matter, was absorbed across of the rumen wall. Regardless, the 16% decrease did not enhance milk energy per kilogram of metabolic body weight. You can see that right below it. NDF, starch, and fat digestibilities were also not modified. There was an increase in the conversion of metabolizable energy intake, metabolizable energy intake to digestible energy intake. So why not the conversion of methane energy to enhanced milk energy? Why did that not occur? Well, ruminal ammonia concentrations were not limiting animal production, which was unlikely to happen because crude protein levels were adequate and MUN levels were not indicative of poor efficiency. So that can't be explanatory. Nitrate reduction could have moved reducing equivalents away from propionate production. And this has some merit considering that nitrate reduction is thermodynamically more favorable than propionate production. Numerical increases were observed in total energy retention over the duration of the study. All right, so again, this is, I'll call it a weak to moderate inhibitor of methane, but there's some, here you have an issue where you're not able to see the conversion of that energy to milk. I don't think anyone's going to disagree that certain species of seaweed are potent inhibitors of methane production. In this study, methane production by cows decreased significantly by 26% at the low inclusion level. This is 0.5% of organic matter of Asparagopsis armata, and 67% at the high level of inclusion. Now, milk yield in this study was reduced with the high feeding level. It's important to mention here. But you also see, my apologies, milk yield itself was not changed, but dry matter intake was reduced. All right, so you often see an argument of enhanced milk production efficiency with dietary supplementation of seaweed. Now, halogenated methane analogs inhibit methane production with a consequent reduction in the abundance of methanogenic archaea. Now, there was an increase here in bromoform, you can see in milk, and there's some other effects on milk component composition. But this drop in voluntary feed intake is a pretty much a consistent observation as well. At least that's from my perspective. Now, some of you might be aware of this article I wrote back in, I think this was in February, talking about, the interest focused on seaweed. There's a lot of scientific merit. There's a lot of excitement. I see it as opportunity. I have high hopes for its success, but there's certainly some concerns we need to think about. The bromoform found in milk is a potential concern. It is below the EPA limits for toxicity, which is a good thing. That seaweed feeding can reduce voluntary feed intake. How's that going to impact sort of animal performance, especially during negative energy balance? Rumen wall damage has been observed by some European researchers. So there's some potential toxicity issues from the animal side. And what about the environmental impact? And so whether you're sourcing this from the ocean, you're cultivating this on land, this is a great example of how we need to think about the complete life cycle of a feed ingredient and its impact on emissions. Because it could look really great at the cow level, but when you look sort of upstream, what does that impact look like? And that includes other things like not just how you're going to source it, but processing it and transporting it. We have to think about this holistically. There's also the presence of heavy metals and iodine, which I don't think has received lots of attention in recent animal science research, but is much needed. Now, fatty acid feeding has been repeatedly shown to inhibit methane production, although I still need to track down the original paper on my major to-do list here. I see that estimates for metabolic use of hydrogen from biohydrogenation are just 1% to 2%. Therefore, it seems unlikely that biohydrogenation itself of unsaturated fatty acids is likely to explain the methane inhibiting effects of fatty acids. However, feeding dietary fats at a high feeding level consistently suppresses ruminal methanogenesis. Now, at a high feeding level, I mean 5%, 6%, maybe 7%. This could be due to a variety of factors that, direct toxicity on methanogens or altered rumen VFA production. In this particular study, dairy cows were fed diets with rapeseed cake, whole cracked rapeseed, or rapeseed oil. You can see that from left to right here. To increase the oleic and linoleic acid content in the diet, so increasing unsaturated fatty acids. Lipid feeding reduced methane production. All right, you can see that quite nicely. All right, it also decreased methane as a percent of gross energy intake. These decreases are typically observed for unsaturated oils and oilseeds and not for animal source saturated fats. there is a feeding of fat scenario where feeding fat independent of saturation has this inhibitory effect. But when you look at it within specific level of saturation, unsaturated fatty acids have the clear methane inhibitory response. There are also medium chain fatty acids like lauric acid that are also inhibitory. And you can overall see a 10 to 30% reduction depending on type and feeding level. However, there's a major limitation, and that is the total fat that you can add to the diet should not be exceeding 6 or 7%. If eating too much unsaturated fatty acids without protection can cause milk fat depression. And in this particular study shown, milk or energy-corrected milk was not modified by the fatty acid or the lipid inclusion in the diet. NDF or crude protein digestibilities and the population of methanogens, which I'm not showing here, was not modified. So that's good. But I'll finish by saying that we need to know how specific fatty acids influence methane production. It's actually a little bit difficult to study. That's within unsaturated fatty acids or beyond. I know there's been some recent work looking at very long chain DHA and the omega-3 fatty acid. It shows some promise. But it's such a complicated story when you think about fatty acids and methanogenesis, because we also need to consider how these fatty acids influence energy partitioning, considering that saturated fatty acids have the potential to enhance nutrient use for milk production, which is not observed for unsaturated fatty acids. And so you could sort of have this benefit on sort of methane production per unit of milk, whether that be through the direct inhibition of ruminal methanogenesis by unsaturated fatty acids, or the enhanced use of nutrients for milk production by saturated fatty acids. So there's probably a lot of synergy that we can evaluate there. 3-NOP is likely the most discussed and studied direct inhibitor of ruminal methanogenesis by inhibiting methyl coenzyme M reductase. In dairy cattle, this reduction averages about 30%. Now, online, DSM argues for a 22 to 35% reduction in dairy cattle. And you'll see an increase in hydrogen emissions, but the effect on performance, robust effects, positive effects on performance are not consistently observed. Some would argue for improved efficiency, which might be 3 to 5% improvement, or enhanced body weight retention. But beyond that, there's not much that happens. But it deserves a lot of attention because its ability to inhibit methane production is consistently effective. It also appears safe for cow and human. Although the research is robust, perhaps I'd like to see more energetic studies focused on 3-NOP, especially under different dietary strategies and heat stress scenarios, but also more measurements of duodenal flow of total microbial and protozoal nitrogen and other nutrients, and the effects of 3-NOP over long feeding durations, and the interactions between 3-NOP and other inhibitors. I am starting to see some of that work, and that's this particular case here that was looking at the interactions between feeding beef cows, my only beef cow study here, 3-NOP at 200 mg per kg of diet dry matter, or canola oil at 50 grams per kilogram of dry matter, alone or in combination. Now, alone enteric methane yield, that's grams per kg of dry matter intake, was reduced by 25% for each of those. This is methane emissions on the left. And the premise here is that 3-NOP treatment typically develops with an increase in hydrogen emissions. And the goal here was to use unsaturated fatty acids as a way to use biohydrogenation as a hydrogen sink for that hydrogen. And the combined feeding of both of the oil and the 3-NOP had a 51% reduction. And that's shown with the green triangles at the bottom. So there was a synergistic effect here observed with both of these types of suppressors of methanogenesis. Now, got to remember that canola is high in oleic and linoleic acid, and this response probably would not have been observed with saturated fatty acid feeding. But again, you have those potential interactions with nutrient partitioning we need to think about. And here, oil feeding also favored propionate production because of reduced abundance of protozoa and fiber-degrading microbes. So there's a lot of potential explanations for the synergistic response that need to be considered. Now, monensin, this is something I often hear about, people talking about monensin and methane inhibition in the same sentence. Monensin is a carboxylic polyether antibiotic that shifts the acetate to propionate ratio toward more propionate and increased milk production efficiency. Most would like to argue that monensin has this anti-methanogenic effect, but meta-analyses repeatedly describe its effects on methane as either being non-existent or at best weak. being less than 10%. From my perspective, it would appear that the effect on methane is certainly due to the drop in dry matter intake. And then, it's there. It's heavily tested. So it all depends on who you talk to, but it's not going to, in my opinion, drops in methane production by monensin are not going to be explaining increased energetic conversion of gross energy to milk energy. It's not going to happen, but somebody can prove me wrong. There is an issue with ionophores and potential resistance. I read a little bit of this research lately, and ionophore resistance is definitely a concern. Scientists argue that ruminal bacteria are resistant to ionophores, even if the ionophores are not fed, and that ionophore resistance seems to be due to physiological selection rather than a mutation. It seems unlikely to have a major impact on the transfer of antibiotic resistance from animals to humans, but it's definitely there. And when we think about, and it's something I'll talk about in a moment here, when we think about feed additives and their potential utility, I think we have to learn from history here, and whether it be seaweed in bromoform or this particular case, we have to think about the consumer and their perception of the technology. There might be a lot of excitement on seaweed right now, but in the long term, what is that going to look like when they start to bring up, potential food safety concerns? Another one that I've learned a bit about lately is essential oils, and I just call it Agla and ruminant. I know there's probably other products, but this is the one that's getting a lot of attention, at least locally. These are a blend of essential oils, containing coriander seed oil, eugenol, geraniol acetate, and geraniol. The typical these inclusion levels are very low, about 0.8 to 1 gram per day. This was a study on the right-hand side by Dr. Mittlener, UC Davis. Looked at basically the absence or presence of aglin. They see increases in milk production. There's so many studies on this. It's fairly consistent. Most of the studies are European studies. That's certainly changing with time. We see increased milk yield in cows producing modern milk yields. We see things like you have to have very long-term feeding to see the effect. Long-term, I mean 5 to 8 weeks minimum to see the methane inhibitory effect. This inhibition is around 8 to 10%. No apparent change in dry matter intake or on milk composition. But, this is a great example of dietary feed additive that really need to understand its mode of action. Like, how is it inhibiting methane? And we would be a bit challenged to define that right now. There's certainly some thought about the VFA patterns and how they're changing, but also focusing on the microbiome. I know at ADSA this year I saw at least one abstract looking at the microbiome in response to essential oil feeding. Now, I call this the kitchen cupboard. Perhaps essential oils need to be on the same page, but there's other examples like garlic, citrus extract, showing that reduces methanogenic archaea populations. What this is, examples like this one are there's a lot of in vitro data out there, and it shows phenomenal efficacy. But when you look at it in vivo, it's the response either is not there or muted. Oregano and green tea extract, that's another example that's out there. I see, no apparent impact on nutrient digestibility, potential reductions in ruminal protein degradation. So let's look at that nitrogen use. Again, efficacy in vivo is uncertain. Cinnamon oil, I couldn't really find that much. No apparent effect though in vivo. But you really need to take, studies. These are studies that are out there. They're robust in vitro studies. There's many of them, but is what I mean by robust. But you have to start doing in vivo studies using a holistic approach, which I'll talk about here in a moment. This is a little summary figure that sort of says where we're at. This was actually completed with the help of the Global Research Alliance. In my opinion, which others are free to disagree, we focus solely on methane mitigation. The current potential additives at our disposal are a bit underwhelming. And you have three options really that inhibit methane more than 20%. We just talked about those: nitrate, 300P, asparagopsis. However, I can argue that they offer little to no performance benefits, that there are potential risk to animal welfare or food safety risk. But there are benefits that are unique to each of those. But the totality of the additives that we're talking about inhibit methane less than 20%. And although the number of published reports to define efficacy are rather limited, I think that's also a concern. We have to start thinking about how these potential additives interact with the base diet, changes in the environment, different management scenarios, feeding level and durations, and many other factors. And this is needed. And this report, I encourage anybody to pull up this report, but they actually had a couple surveys that I found really interesting. And this one, they surveyed feed additive developers, and these companies were in the business of selling probiotics, tannins, essential oils, spirogopsis, nitrate, and antibiotics. And when asked what type of countries the company is currently or planning to target, the clear majority said the developed world with a focus on dairy and feedlot cattle. There was little attention on the developing world. And it was clear that supplements would do little to reduce methane emissions in the undeveloped world. This suggests that we really need to consider how base dietary ingredients that are specific to given regions, different forages, can enhance efficiency or have bioactive nutrients within the feed that inhibit methanogenesis. What I found interesting is that these developers realized that data focus on methane emissions is only part of the research interest. Mode of action within a focus on the microbial response, dose and duration, residues in meat and milk, and impacts on animal health are all important. And it's hard to read that, but that's in the bottom left. The main constraint identified for the commercial release of new tech was research and development. So the scientific community needs to develop infrastructure for the proper R&D of tech through strategic academic industry partnerships and perhaps through farm engagement. Developers are also considering chemical discovery, registration, and marketing is the number one challenge. We'll come more on this in a moment, but it was concluded that we need more discovery of novel products, and information about high efficacy of compounds can often be misleading. In a similar manner, the same report surveyed cattle producers and managers. Most of these were in Brazil and Indonesia. It was a small sample size. One-third had 1,000 head, one-third had over 1,000 head, primarily beef cattle operations. The majority source of their information for these producers directly came from the supplier. It is imperative that suppliers avoid greenwashing and present independent research data. I'd like to see more research trials or product-to-product comparisons as well. That is certainly going to be difficult to achieve if we're not going to rely on industry support. These farmers were predominantly using rumen modifiers and probiotics and did so for the purpose of enhancing animal performance. Their goal here was not to reduce greenhouse gas emissions. In fact, 92% of these producers said that animal performance and feed efficiency motivates them to use motivates them to use products that reduce greenhouse gas emissions. It's all about animal performance. This emphasizes the need to study energetic efficiency of feed additives if we're thinking about methane inhibition. Because as you can see in the middle panel, right, farmers are willing to pay, but they need accurate information, and the product needs to enhance growth, lactation, or health. So I have a few more slides here thinking about where we need to go next. And we need to start with what we're currently doing and analyze that. And I call this an atomistic approach, where basically it's an approach where we're going to study a potential feed ingredient. You usually go into this saying, I'm going to look at methane. I'm going to look at methane emissions. I'm going to look at crude protein digestibility, NDF digestibility, and milk production. And that's it. And then we move on to the next study. And then we try to piece it all together. Well, now, if you have this approach, this is an approach that looks at a single greenhouse gas and ignores other emissions. I will say the clear totality of the work is looking at enteric emissions and not considering manure emissions in the same study. Efficacy, the mindset of having that efficacy is not influenced by feeding duration, host or microbial genetics, nutrition, or environment is going to do us harm in the long run. And so just because you have a study that shows X% decrease doesn't mean it's going to apply when you have these other variables change. This type of approach relies on relative or qualitative efficacy, and that would be considered adequate. That ruminal adaptation or compensation by the microbiome is not a concern. That changes in energetic efficiency are not measured. And the metabolic fate and residues in meat and milk are not considered. and probably the hardest thing for animal scientists, but the life cycle assessment of the ingredient is not being evaluated. This is, I would argue, and this is not always the case, but when you just challenge you to look up a paper and see if any of these apply in that particular paper. And, I always tell my students, I tell myself, I can always do better, and I think we can do better with our approach moving forward. And so one thing we've been trying to advocate for is a holistic approach when we want to define methane inhibiting feed ingredients, the efficacy of them. What is this kind of approach? Well, it's an approach that considers the effect of the ingredient on its ability to inhibit enteric and manure methane emissions without increasing other greenhouse gas emissions. Maybe nitrous oxide emissions would go down in manure too if we measured it more. But we need to think about the complete system. This type of approach will look at efficacy as being influenced potentially by feeding duration, potentially impacted by host or microbial genetics, changes in nutrition, forage source, forage quality, or changes in environment. This type of approach would see relative or qualitative efficacy as being inadequate, and that we need fully quantitative data, especially with regard to greenhouse gas emissions. And that this type of approach says that ruminal adaptation or compensation is potentially likely and requires attention. We need to think about the energetic conversion of gross energy to milk energy, and that we need to measure the metabolic fate of these different additives. Look for residues in meat and milk. It has to be a high priority. We need to share that information with the consumer. And a personal struggle that I've had, life cycle assessment of the feed ingredient is also important. Like, I want to be studying things that are going to have sort of major benefit, not just at the cow level, but everything upstream. It has to be environmentally friendly. Otherwise, we're not going to make real progress. So how do you define efficacy using a standardized holistic approach? Well, there's a lot of talk now about creating standards. International standards are important, but what kind of measurements should we think about? Well, total enteric and manure greenhouse gas emissions. And you can see the list there. That's the common list that everybody talks about. It has to be fully quantitative. We have to look at the conversion of feed gross energy to fecal, urinary, methane, digestible, metabolizable, and tissue or milk energy. Looking at duodenal nutrient flows. You have to understand mode of action. I've talked to a lot of farmers, and I've talked to people in feed that are developing new compounds, and everybody has this interest. But too often you want to look at the performance, you see a performance outcome, and we can't explain it. I think we need to explain it. Again, this also comes back to consumer buy-in to these potential new technologies, and we need to think about total tract digestibility, whether it be ruminal, post-ruminal, as well, of different nutrient classes. We need to look at feeding level and duration, look at the economics behind it, look at the practicality, feasibility, and its accessibility at a regional level, looking at changes in rumen ecology and fermentation, changes in animal health, looking at compound absorption, degradation, excretion, interactions with the diet, environment, and genetics, and any potential things of human safety concern. But most importantly, we're going to try to solve this problem globally. There's labs all over the world doing this, been doing it for a while. We all need to get on the same page in terms of international standards. Now, we could start by talking about different types of methods to measure methane. I'm going to tell you right now, there's no perfect method. If you think there is one, you're wrong. And there is going to be a need for a combination of methodologies. Respiration chambers, I'm going to talk about in a minute, they're a high cost. There's a high running cost, lots of labor, but they have good repeatability, but they're low throughput. And certainly you put an animal inside of a chamber, you're going to change behavior. All right, SF6 technique, which I talked about briefly, little less cost there. Running costs can still be high, still have labor, still can change behavior. Repeatability is medium. Different types of system. The green feed, that's the common one everybody talks about. Cost is also low. They're probably more mainstream. You're seeing more green feed systems maybe on commercial farms, commercial field trials. That's great. But when you look at this big picture here, I think we need, again, it comes back to international standards. It also comes back to validating sort of efficacy using multiple methods. Respiration chambers might be considered by many as a gold standard, including myself. But I can't run 80 cows through a respiration chamber very easily. Okay. And these also systems don't exist everywhere. They're going to be very limited throughout the world. And so we're going to have to rely on these other methodologies to define efficacy. Now, I want to talk about chambers in a bit because that's the direction I'm going. They provide a clear advantage to measure total gas exchange. That's from both ends of the cow. However, recent data has definitely brought to light a serious issue that needs to be addressed if we were to define efficacy. We need to think about measuring the concentration of gas at the outlet and inlet when combined with flow rate. That does give us the ability to measure total emitted gas rate, for example, methane. And that certainly involves calibration tests for flow meters and analyzers, but we need to think about whole chamber calibration tests. The principle is to provide a continuous flow of a known amount of gas using a mass flow controller for overall chamber emission measurements. This accounts for any losses from the chamber itself, but also sampling issues due to flow mixing behavior in the chamber. Other tests are performed to determine ducting efficiency when the source of calibration gas is provided directly in the duct. Now, they've done some studies here, and the combined approach provides a measure of total system efficiency. And in reality, you want this to be 100% or 1. But in this particular study, they had 6 chamber facilities and 22 individual chambers. And the ducting efficiency ranged from 0.7 to 1.2. Chamber efficiency ran from 0.9 to 1.1. And the full system recoveries of gases in these chambers ranged from 59 to 115%. And ducting was the largest source of variation. That's incredible. This is published data. In a recent letter to the editor of JDS by Garrett 2018, they observed that 73% of publications in recent JDS volumes failed to report recovery tests. Regardless of method, recovery tests should be performed before and after each experiment, and most importantly, reported with the publication of results. Well, what are we doing here at Cornell? There's my face, others that you know, including Mike Van Amber, Kristen Reed, and Jingen Lay. There's our dean, Ben Holton, Tom Overton, and Daryl Neidham. We consider this is really the sort of the leaders of this initiative where we're thinking about how Cornell is going to contribute. But we're working with engineers, we're working with people in global development, we're working with ecologists like Bob Howarth. The Atkinson Center for Sustainability is really supporting us in terms of helping us connect with NGOs and financial opportunities. And we obviously have ProDairy that's going to help us extend our discoveries into rapid translation. And we're interacting with our Institute for Digital Ag to identify ways to provide our data to the public once we start to generate it. So we had to think about our working goal and strategic plan. We want to reduce global enteric and manure methane and nitrous oxide emissions from cattle production as a means to mitigate climate change. This is really a working goal and strategic plan. I would argue nothing's quite locked in just yet, but we certainly want to discover and facilitate the regulatory approval of feed ingredients to inhibit enteric and manure methane emissions. We want to identify and accelerate the adoption of manure management practices that lower methane and nitrous oxide emissions and nutrient runoff from farms at different scale. Our own dean is looking at innovative soil management practices to enhance carbon sequestration. And something that is gaining some interest internally is how do we enhance the efficiency of nutrient use for milk production in countries like India, and do so by enhancing ruminant ration balancing and feeding recommendations for Indian dairy farmers. And most importantly, in tandem, we're working to develop and execute a communication plan to educate the consumer about advancements in sustainable animal ag. Well, the catalyst for this change was we're approaching close to $2 million in support from Cargill, sort of seeded that money, but also New York State and other donors to acquire 4 respiration chambers. The facility is currently being renovated adjacent to Morrison Hall, and this will be operational in next year, hopefully by summer. This is going to allow for real-time 24/7 greenhouse gas measurements, oxygen consumption, allow us to estimate heat production, and perform indirect calorimetry. They're going to be climate controlled from 30 degrees Fahrenheit, so slightly below freezing, to 105 degrees Fahrenheit, so heat stress scenarios. And we're thinking about gas recovery systems. That's what you see in the bottom right. We're also acquiring green feed units. We have current funding for 3 green feed units. Most of the funding here came from New York State, $160,000. We also have some donors we're working with. This is going to allow us to perform high production trials, just like many other universities, sort of behind the game here. both in a freestall and tight stall scenarios. But most importantly, if you have an 80 cal production trial, 20 cows per treatment, 4 treatments, we'll probably pull out a subset of these animals, put them in the chambers, sort of validate our green feed measurements, but also be able to get the production data we need. Most recently, myself, Mike Van Amberg, have received funding from the Cornell Center and Environmental Defense Fund. My PhD student that graduated, Dr. Ananda Fontoura, she's going to stay on as a postdoc. And our goal is to identify barriers for the timely adoption of feed additives and drugs that inhibit methanogenesis. And our main contribution is to help define the gold standard methodology that will demonstrate the holistic efficacy of feed additives and drugs to inhibit methane. We realize that other people are doing this with the goal of influencing the FDA guidelines and approach. We've had conversation with AFIA, and we know there's going to be more money on behalf of their efforts directed towards the FDA in the future to enhance staffing. But we're just starting to partner with the Global Research Alliance as well to think about that standardized methodology. Overall, we have at least 3 postdocs, so probably a bit more over the next 12 months that are going to work on this. The end goal is that we have standard methods, but we also create a formal recommendation to the FDA. I'll finish with these last 2 slides here that where are we at now in terms of we're trying to build personnel. We have some personnel that already started to hire. We're thinking about facility infrastructure that we need. We're going to be very busy. There's no question about that. I'd argue we're very busy now, but we're going to be we're playing a different game here in the next 12 to 24 months. And so we need to have the infrastructure and people to prepare for that influx. And we need to embody that holistic approach in everything that we do. And so we're thinking about high throughput ways to identify new compounds. And then that is a way you can use in vitro approaches for that. But to get a rapid answer, then eventually get to in vivo testing quicker. We do think that new compounds are needed. We also want to really think about how we train the next generation of students in animal nutrition. So, there's a lot of bomb calorimetry that you need to do a lot of those energetic measurements. Using mass spec, looking at carbon and nitrogen use. There's an opportunity here to train our students, but also train international scholars, perhaps from India. We'll see, to be better animal nutritionists. We need to prioritize data management for the benefit of all. And so how do you take critical data? Maybe there's only so many institutions that will have chambers. How do you make that data accessible to many people? And how do you do that within the confines of sort of industry-sponsored research agreements? That's going to be a real challenge. We're building up philanthropic and industry support. That's happening by the week. It's incredible. We hope to share more in the immediate future about all these efforts and where we're going. But we will definitely want to ensure scientific transparency through public engagement. We actually just got an NSF grant to learn about how to do that better. And we want to look at that regulatory approval process. We're at least in strategic alignment with it. Definitely improve our models that we're working on, like Kristen Reed's Rufus and Mike Van Amberg's CNCPS, and look at how we can strategically coordinate and collaborate at an international level. I'll finish with this, that in the absence of a holistic scientific method and transparent data, the efficacy of methane inhibiting feed ingredients, additives, or vaccines or drugs, whatever you want to call them, should be considered with cautious optimism and perhaps skepticism. I think I can be quite a bit skeptical sometimes, and I really want to challenge my own findings. I want to challenge other findings, but I think we need to be optimistic. But we need to be critical. We've got to be critical of ourselves from day one. We need to study the complete system. We need to compare products with other products. Data needs to be made public, transparent, and the consumer needs to be aware of the pros and cons. We simply don't have time to waste. Here's a list of all my major support. Working on all kinds of things right now, looking at nutrient partitioning, the role of insulin with our NSF support, USDA supports looking at lysophospholipids and how they influence metabolism and immune function. Our FAR work is looking at sort of the energetics of heat stress, but a lot of industry support as well, and most appreciated. I'll take any questions. Thank you for the opportunity to speak.
Okay, that completes the presentation part of the webinar. Following is the question period from the morning webinar and the afternoon webinar. Firstly, thank you for joining us. As a reminder, today's slides will be available as a PDF document for download from our website. That page will have links to the recording and the PDF presentation, as well as a link to the PDF Joe referenced on the efficacy and applicability of methane inhibiting feed additives for livestock. Also, I do convert the audio to podcasts. You can find those under the podcast tab on the website or subscribe on Apple Podcasts. In the morning webinar, I was joined by AMTS Italian distributor Elena Bonfante of Dairy Innovations Italia. AMTS team members Tom Taluki and Lynn Gilbert also helped during the question session. Our afternoon question period was hosted by Marcos Neves Vieira of the University of Lavras in Brazil, AMTS China distributor Sean Lee of AnSciTech, Lynn Gilbert of AMTS, Paula Turillo, and her very capable translator, Miriam Strauss, joined from Afina in Argentina. I have wonderfully supportive sponsors who allow us to pay our speakers and to justify my time commitment to this project. We thank our gold sponsors, Arm & Hammer Animal and Food Production, #ScienceHearted, the Canola Council of Canada. Learn more about feeding canola at canolamazing.com. Adina, experts in animal nutrition with expertise in plant bioactives, and Protetka, transforming the future of farm animal health. Our silver sponsors are the Forage Analysis Labs of Dairyland Laboratories and Dairy One, both with affiliates around the world. Adiseo, ruminant nutrition solutions to ensure animal performance, and Novamil from Novita Nutrition. Our bronze sponsors are AminoMax, Virtus Nutrition, Origination Inc., Balchem, and Glucobest. Each of these companies support education and research worldwide. We hope that you consider them in your formulation decisions. I remind you to look for the final in this series from Dr. Tom Taluki in September 2022. As a bonus webinar outside of the Nutritionist, we have a Canola Council of Canada webinar featuring Dr. Chayuchi Benchar in October. He will also focus on emissions. Now for both question sessions. Before Tom talks, because Elena is on a bit of a tight schedule, I am going to say, Elena, would you like to ask some questions?
Hi, Marianne. Thank you very much. Yes, I have some questions for John. Thank you very much for the great presentation, John. It is very informative, and I think now this is actually the present and the future of our industry. So I have a question related to the study that has been done on the canola oil supplementation. And if they considered, of course, the correct amount that will be good for reduce the methane emissions, related also to milk quality. So which is the level until you get a good milk component and is not going to get detrimental for butter fat, for example.
Thanks. Before I answer that question, I'll just say that I did share a link with the PDF report to the Global Research Alliance. Those were 3 of the slides that came out blurry. I was sort of in the last minute hustle to get this completed. I apologize, but that PDF report will be sent, I'm sure, to all of you, and that you can look at and zoom in on those figures. Regarding canola oil, I mean, it comes back to just, I guess, probably fundamentals in terms of how much unsaturated fat you should feed. I mean, I'm not the one who did all this work, but if you look at work from like Adam Locke or Jenkins or others, I mean, they've sort of characterized the rumen unsaturated fatty acid load, and there's a general understanding that 3.5% max is sort of what you should be feeding at in terms of, on a dry matter basis, obviously, in terms of linoleic and linolenic acids. Oleic acid is not so much a concern. I know there's a lot of commercial fat products on the market that are high in palmitic and oleic, and I guess I'd be a little bit, you probably can ramp up those a little bit more than you would sort of traditional oils, but I think that if you follow that fundamental rule in terms of not exceeding that 3.5%, I think you're going to maintain rumen function, and you're going to sort of maximize that inhibitory effect on methane. I think there's just sort of a lot of work, though, that sort of needs to define that, but if you don't want to impact nutrient digestibility, cause milk fat depression, et cetera, I would just stick to that fundamental rule for now. Now, I'll say one other thing. There's a little exception to that rule, and that you have different types of protected unsaturated fats. We can probably talk all day about types of protection, but like calcium salts provide some degree of protection, and maybe there's some wiggle room to that rule. And then there's also things like DHA that's showing some promise, where you might only need to feed, 10 grams or so of DHA to have an effect, because it's highly potent. But a lot of those things need to get teased out.
Thank you very much, Joe. Another question is more on the economic side. So I've seen that some strategies are based on common feeds that actually you can add to the diets. But have you done also an evaluation of the economic, so the cost of very good diet that is that has the goal to reduce methane emission, and if it's gonna have a return, let's say, for the farmer, and also if the dairy industry is willing to pay back for the extra effort, let's say, in US at least.
Yeah, you realize I'm an animal scientist, right? Animal scientist, like I was just creating a diet the other day, and this is a dream diet that probably will never actually be fed in a real scenario because of the cost. But, I haven't looked at the economics. That's not my area, but I'm sure many people are. And if you pull up in the report that I share you, they do look at sort of the estimated cost for these various feed additives, if they're on the market or could be on the market, and what might that look like. But you're absolutely right that in that report, I mean, it was clear that 92 or 97% wanted the enhanced performance to get the economic return. And so I think economic return, I mean, at least in the United States, is going to be purely driven by energy corrected milk yield until something else changes on the regulation or incentivized, or farmers are incentivized to use it in some way. So in the US, that ain't going to change anytime soon, I don't think. Probably going to change in other countries. But I think there's a bigger issue. The bigger issue when you look at globally is back to those developing nations, because in those scenarios, they're not going to go out unless it's something like I was just learning a lot about India. Like India is creating these trace minerals sort of packs that they're going out and giving to all the farmers. So it's coming from the government. If there's something like that, yes, but is that going to include a methane inhibitor? Unlikely. And so any kind of feeding strategy is going to have to use just common ingredients. And so I think there's got to be some improvement, especially on the plant breeding side, to solve some of that, to have wide scale adoptability.
Thank you very much, Joe.
All right. Excuse me. Thank you, Elena. Elena, I'm just going to put a plug in for a webinar that I haven't really spoken about much yet. We will in October have a Canola Council of Canada sponsored webinar with Chayoki Benchar, and he works specifically on emissions. So there may be some additional information with regards to your question about the canola study. And if you want to join as a co-host on that, you are so welcome. It'll be, I think, 10 o'clock our time. I'll get more information out. We're just putting that information together. Before I go to some of the questions or ask Tom, I'm going to pointedly do a little plug-in for AMTS and then mention something that Tom was thinking about and working on a little while ago. First of all, Joe mentioned that there should be an increase in nutritional teaching and maybe specifically use of the CNCPS because it allows for precision feeding at university level. And I just want to say that we offer the program to any university that wants to use it for use in teaching free. So anybody out there listening in our attendees that is associated with a university or wants to contact their local university, please reach out to us and we'll make sure that they get the program. And then Tom, you showed a diagram of intersecting desires, I guess, a few months ago that I remember. And one of them was, how is it, you had a term for it and you're going to explain it better than I, nutritional performance, economic performance, and environmental performance, and the intersection there too. do you want to talk a little bit about that, or ask Joe some questions with regards to that?
No, because I don't remember. I don't remember the diagram, so
Yeah, it was
I'd have to go dig through it
yeah,
and find it. Yeah, I don't know.
yeah.
Sorry,
How many brain cells were affected going to South Africa?
way too many.
Mm, mm. Tom, do you want to field any questions, or shall I go to my
Keep
questions?
going. No, keep going. Keep
Okay.
going.
I'm going to tackle, Joe, some of the questions that I see in the window and a few that I wrote down. Let's start with the first one from an anonymous attendee. Are greenhouse gas emissions due to concentrate production higher than methane mitigation due to concentrate use in dairy nutrition?
Yeah, unless I'm missing something, the answer is no. I would say that there's one of those earlier slides. I saw this question. If you go back to one of the very earlier slides,
Yeah.
in terms of feed production itself is going to be substantially less in terms of enteric methane emissions when you look at the complete system. Now, I think there's certainly some issues with that, though. I mean, you think about I'm using my low efficiency country scenario again, because in that kind of scenario, you're going to have so many animals. There's a higher number of animals. We're talking about three times as many bovine in India, but there you've got a scenario where they're not going to be able to produce the amount of concentrate required to meet the energetic demands of all those animals. And so in that particular case, where are you going to get the energy from? And so something's going to have to change where animal numbers are going to drop, or they're going to be importing more. And then what impact does that have on total emissions? Now, I think back to the actual sort of look at the particular crop. I mean, there's probably some unique cases there. I mean, rice obviously is a major concern in terms of methane production. And so, but when looking at it on the basis of corn, for example, not at all. I mean, it's going to be enteric fermentation that's going to be the main driver.
Okay. All right. Thank you. And I don't know if I slid to the right slide for you. Just Joe,
yeah.
Go ahead and direct me as to which slide you want me to go through. Let's see. The next question is from Ron Solomon. What is the best system or methodology you are recommending to use on semi-commercial farm for CH4 measurement? And he regarding accuracy, but also practicality for multiple cow measurement.
Yeah, I've only started to give these methane talks, and it's hard because there's a lot of people want answers to these tough questions. And is there something out there right now that could do this on a wide scale? I don't believe so. I'll say that there's two things I can respond in that. So this AFIA, Nature Conservancy, they have there's this group called iFeeder. I think some of you probably know what this is. And they're going to start doing commercial field trials with things like essential oils, et cetera. And one of the key questions is, how do you measure that? And I know a lot of different green feed systems that are going to be applied in that kind of scenario. I mean, the green feed, from my perspective, it exists in many places across the US, at least. I've actually just went over to Switzerland. They're installing them over there. So it's a technology that is spreading. And so then you can do repeatable studies using the same methodology. That's a benefit. I think you can put those in a freestall scenario, which is beneficial. You can get sort of high sample rate in any kind of pen. There are some things, though, where we got to make sure we do those. So I talk about gas recovery tests on chambers. You got to do gas recovery tests, I would argue, on any method. And so we need to have those standards sort of published and followed and adhered to. So, yeah, I know there's other work, like looking at the whole farm scenario. Like, I had somebody come talk to me about lasers, like putting drones up above the barn and all that kind of stuff. I'm not familiar with all those technologies, but I mean, that's not going to be helpful to looking at individual pen emissions. So you're really going to need something in the pen. In the green feed system, you can attach it to the back of a trailer and roll it out into a field somewhere. So that also has a lot of benefit for grazing operations.
Okay, thanks, Joe. And I'm sure this is going to be an area that will continue to change and evolve, and one hopes improve. The next question from Akim Hoffman. First of all, Joe, thanks for the excellent presentation and giving your insights. His question is about the impact of forage quality, corn and grass silage, on CH4 emission results. Is it only the lignin content we need to consider? What about the impact of silage inoculants, indirect or direct? Thank you.
Yeah. So, I mean, obviously I look at everything often from the perspective of starch and sugars. I mean, anything that's going to enhance propionate supply is, I think, is where those gains are going to be made in terms of methane reduction. In terms of inoculants, I can just tell you right now that it's going to be a weak efficacy. I mean, I don't know too many studies that have shown methane reductions beyond like 10% with silage inoculants. I will say that like fibrolytic enzymes is something else I'd put in this category that's often talked about. Those can, yeah, hopefully improve rumen fermentation and enhance digestibility. But again, I don't see a convincing body of data yet that shows conclusively that there's marked reduces in methane. I think part of it is just not enough data, but at the same time, when you look at the existing data and you see a 10% reduction, I don't think this is going to be the game changer we need, but it's something that you could add in addition to other dietary approaches, hopefully, to sort of maximize the response. That's where we got to get to, because we have a lot of these tools of the trade that are going to be in the 10 to 20% reduction, but how do they work in unison to sort of optimize the inhibition?
So Joe, I had a question on that life cycle assessment, and that taking that a little bit further, what about the land use? Quite often the argument in support of ruminant agriculture is the fact that it utilizes land that is not otherwise able to be cropped on. When you go to the types of forages that can be grown on that it's so complex.
Well, you have to look at this this is just a very broad answer to your question, which is probably a very complicated question.
It is.
Yeah. But I will say that we always have to, and I think that the conversation is changing, where you base things on nutrient supply in terms of nutrients, the availability of nutrients for consumption by humans, right? So looking at emissions based on nutrient supply in that regard. So that's positive. But I shared this with you prior. We're doing a little mini project where we're using, I never intended to use hydroponics as a way to grow fodder. But as I learn and talk to more people in Asia, for example, where this technology is becoming more prevalent, and I know there's at least some interest in Southwest United States, but there's a lot of these companies popping up where you can grow this grass vertically. There's a lot of limits to that. I mean, there's probably some sustainability benefits there on water use and less land per unit of dry matter, but at the same time, you don't gain any dry matter in those systems because it's just this amount of dry matter in the seed, and you actually lose a little bit. But we're hoping to see improvements in digestibility and just a lower carbon footprint. But you can only maximize so much fresh grass you put in the diet anyways without dropping intake. So I'm getting on a tangent there, but there's probably some benefit there for those kinds of technologies. But again, this also comes back to scenarios like if I have some collaborators in China, and they'll often sort of wish they had the kind of corn silage that we had in the United States. And so there's got to be, and this is, I don't know how you do this, there's got to be a regional sort of focus to this problem. And unfortunately, in a lot of these countries that have poor quality forages, I'm not sure there's the scientific infrastructure or to sort of to help solve it. So they need our help in some way. And God, that's not an easy answer to your question, but
It's not an easy question to answer, Joe.
Yeah.
What you just said about the forages is a great example of, we're extremely lucky in the Northeast and in the upper Midwest and Ireland with the amount of research that goes on relating to forage quality, forage species, and that doesn't exist in the rest of the world. And that's a huge limitation. And yet, if they try to turn to us, and this is always the challenge that you're alluding to, is if we start talking about, some of the forage things that we do, in the Northeast as an example, and try to apply that in Texas or South America or anywhere, the differences in climate, the differences in soil, the differences in everything. We can give some general directions, but all of these things with forage quality are so locally dependent that it's an extreme limitation on doing things.
Well, we've had a lot of interest in talking
Joe
about
froze
for a reason. It's
Yeah, Joe, you froze. Can you start over? I hope it's your end, not my end.
Are we good now?
Yeah, turn off your
Yeah.
video.
Yeah, I'll just say saying there's a lot of interest internally here on India and what we could do. And it's a great example where they don't really have the commercial lab infrastructure to do wet chemistry, like to do the methods that are required to analyze feed chemical content. And they don't have them. I don't think, they've got some personnel there, but they also need some training opportunities. And so how could Cornell help with that? And so at least we better understand the feeds that they have at their disposal and then put that into our feed library. That would be awesome. And so if anybody out there that has any ideas that could help in that regard, I found it really challenging, but Mike Van Ambrick's helping me out here to try to figure out how we can do something in the short term, at least on some sort of pilot case with some internal support that we could potentially garner.
Okay, thank you, Joe. Thank you, Tom. I'm going to ask a question, butt in with a question, and then Tom, if you want to work further. This is another question from Akeem. There will be, what will be an approach to get the farmer to use CH4 reducing agents if there's no direct payback from milk yield and fitness? Yeah, I think it's like make it an added bonus. Yeah. But anyway.
Yeah, I don't know how to answer that question. I mean, get the FBI to show up at their door or something. It's not going to happen.
No, I mean, the only way that it would be if we were regulated. And we don't want to go down that path. And it annoys me to even think about that, since, you look at the methane that cows produce, the vast majority of it is really recycled carbon. So they're picking on us because methane's is so powerful, and we can reduce the heating potential because of its relatively short lifespan in the environment, and there's not a lot of us in agriculture, so we're easier to control. And that's not tackling the bigger picture.
Yeah.
Joe, I got a question. Oh, wait, I want to go back to Akeem. Akeem, it's not lignin. It's a combination of the lignin and cellulose content of the forages. So it's you just can't look at one or the other, one component of it. Joe, are there anything that you see on the horizon that excites you in terms of methane mitigation strategies?
Oh, I'd love to answer that question for you. There are a couple of things that have a personal interest that we need new types of inhibitors. Depending on who you talk to, I've talked to a lot of these different NGOs, and they'll say, well, there's so much data out there on these existing inhibitors that are out there, but there's nothing that's robust, that's beyond 30%, that really excites me. And if you read my article, seaweed doesn't excite me. I think that's the type of inhibition with enhanced performance that we need. And I think what excites me more, and I go back to the interactions, because if we don't make any new discoveries, we really have to think of how to target the multiple hydrogen sinks, do direct inhibition in rumen modifiers. How do you look at the synergy? But there's a real problem, and there's some industry people, I'm sure, listening to this, that has to be overcome. And a lot of that research that is funded and supported, there's often this I don't know what you want to call it, ideology or whatever, but that you're going to focus on that specific product. And there's not a lot of, hey, let's work together kind of thing to see how we can sort of optimize this, because realizing that, hey, maybe our inhibitor only works 10 or 20%. That's what we got to do in the short term. And I hope to share some new stuff too that we're working on alternative inhibitors. And so we're really setting ourselves up here to do high throughput screening of compounds. Because I think that's what we got to do. You said something.
All right, let me throw this one at you too. If someone says 10% inhibition, how much faith do you put in that value, especially when you stated that, none of the trials actually report, the vast majority of the trials don't report what their initial and final balances were. Is 10% an artifact? Is that just is that within the statistical range of not different from zero when we put everything together?
Yeah, I see some claims out. I've seen claims, oh, I got a 4% reduction. I'm like, why bother in that particular case? So I think these 10%ers that are showing up, like I'll say, for example, the essential oil one. I mean, that one has a lot of repeatability across independent studies, gives me more confidence. But unfortunately, with a lot of these plant-based extracts, there's just not a lot of repeatability across studies. They'll put out 1 or 2 studies, and that's what they rely on. And I have a lot of concerns about the variance when it comes to methane emissions, just after talking to Dr. Kononov, because you can have a scenario where you've got high producers and low producers in the herd in terms of methane, right? High methane producers and low methane producers. If you were to take those, and there could be potentially 20, 30% difference in those groups. If you take those 2 groups and you look at the efficacy, you could have a scenario where you could have a totally different response. So I'm pretty confident in that. And so that's concerning. Like one more rant on the in vitro part. There's been some work suggesting that if you go out and just take some naive rumen fluid, you throw some different types of compounds on it, you get great efficacy. But if you go out and you put that same feed additive in the cow for a couple of weeks, and then you come back and you take the rumen fluid and you look at emissions again, you don't see any response. So first off, I don't believe in any in vitro data at all until it's proven in vivo. And just realize that there's a lot of variance across that herd. Don't anticipate that the environment, like it gets hot in the summer, you're probably going to get a different response. We just don't have. You realize we're talking about like single-digit number of studies there. Very inadequate.
Yeah, absolutely. And the thing that gets me is it kind of shows some people's in society's arrogance that we can easily modify something over time that has taken thousands of years of developing a symbiotic relationship to maintain a healthy rumen and a healthy cow, and utilize these feed types that we use, and for us to try and modify that within, hell, I'm going to say even within 25 years, I think is going to be a phenomenal timeline for us to do anything.
But there's people and there are groups that will write an email and say, can this be solved in 2 to 3 years? Like, that's what they're thinking. Like, I just don't see it. So
I know. No, not at all.
I'm gonna ask a question from Reza Lofty. What's your opinion about holistic approach in ruminant nutrition?
Yeah, I mean, this is what I've been advocating for last year or so. I mean, this is no discredit to the animal scientists that have done great work over the last 50 years on looking at methane inhibitors. But, the reality is when you have only the resources at your disposal to do a study. And in many scenarios, especially on the methane measurement side, I would argue a lot of the methodologies are inadequate to look at total emissions. You might have the funding to go out and look at it, NDF, crude protein digestibility, milk production, and methane measured using SF6. Well, you're ignoring all the other gases. It's not fully quantitative. You're not thinking about how the adaptation is changing with time. It's going to require a very significant investment. You can think about the regulatory approval process to get something approved in the United States. It's going to have to require extensive, high dollar amount research to pull this off. And so when you're talking about a plant-based extract from this small company X, they're not going to have the money to do that, to really prove efficacy holistically. And so that's going to be one of our limitations that are going to have to be overcome. And there's going to have to be some non-industry support somewhere along the lines to help them out, because it's just not going to come to fruition.
One of our listeners put a link in the Q&A session. It's the Institute for Feed Education and Research is doing a lifetime assessment webinar. And the registration is there. That'll take you to a page to register if you're interested in getting more information. So just to point that out to you, if you don't have your question thing up, you'll be able to see that. And Tom, Joe, anybody more questions? There's undoubtedly, this could be talked about for a long, long time. Yeah. There was some, what about the effect on dry matter intake on some of these compounds that are recommended?
The ones that, I'm just repeating myself here, but the ones that probably have me the most concern would be things from unsaturated fats, seaweed, tannins. Those, when you feed too much, you're going to drop dry matter intake. But too much of anything, right? That kind of mantra. But those would be the top three probably initially that would have me concerned.
Okay, thank you. Yeah, listening, just thought that as potential as well. Tom, any thoughts, questions before we close out for the morning?
No, I think we're good.
All right, Joe, thank you so much. Lots of kudos in the comments. So thanks so much for joining us, and we'll see you tonight. Yep. I'm gonna just to remind you, I will put a link to the paper in the recorded page. And also, I'm going to see what I can do about improving legibility on some of the things between the now and the next webinar for the benefit of the people who will be joining then. So
what time is that, by the way?
So for me, it starts at 5:30. I start running the recording at 6. Okay. You can expect to need to answer questions right around 7.
Right. All right. I don't think I have the Zoom for that. That's why I asked.
What I do is, because Zoom doesn't allow me, I don't want people to have 2 different links. I go in and I edit that Zoom link to have a different time, and you'll get a notice as soon as I do that.
All right. Thank you.
Thank you. All right, everybody. Thank you for joining us. Welcome, everybody. Welcome, Joe. I don't know if you want to run your camera or not. Let me make sure that we can see it.
I'm here. For some reason I short out. I'll just turn off my video, and I will do my best to talk slow.
I know. We all have a tendency to just go as fast as we can. I am going to wait for some questions to come into my question and answer window. If anybody has any, please write those in. But while we do that, I'm going to go first to Marcos Neves Piera. Marcos, welcome. And Paula is always busy trying to do her translating, so I try to get somebody else to answer first. So Marcos, how are you today?
Pretty good. Thanks, Miriam. Thanks, Paula. Thanks, Joe, for the talk. I think very interesting, very nice slides. Actually, I have a lot of questions here.
Okay.
And good night, everybody.
All right. Thank you for joining us, Marcos. Sean, I'm going to put you on the hot seat too and see if you have any questions you want to ask. I know that you'll be contacting Joe about the potential for doing a webinar, answering a few questions in China at a later time. But Sean, welcome.
Hi.
Hi.
Good evening. Hi, Joe. Thank you. It's an excellent presentation, very informative. I learned a lot. Also, I agree with you about the conclusion. I don't have more questions.
Well, I'm more than welcome to give a webinar in China. Now, my wife told me though, this last Christmas, I gave a webinar on Christmas Day, and
Okay.
my wife said I can't do that anymore.
Okay. Oh, I am scheduling that, but for sure it's not on any holidays.
Okay.
It's bad timing. But China don't celebrate Christmas Day, so guys may not
I still did it.
might not pay attention there. Yeah. The
Joe,
very excellent presentation today. Yeah.
Joe, there's always the possibility of saying no, pick another day.
Yeah, I don't say no very frequently.
Yeah. Well, I appreciate that you said yes to speaking for us tonight. I'm going to give Paula a few more minutes. I have a couple questions. Coming back to this, and I'm hearkening back to some of the talks that we've had in earlier presentations this month, but looking at this chart right here, and it always comes down to dilution as the solution. And sometimes we look at where the problems are and where the efforts are going. And you did talk about it later in your presentation that the feed additives are all focused on Western style production, and where there's already sort of a very big focus on efficiencies. And those Latin American and the Caribbean and South Asia, those big wheels, they look like they're places where in the big picture of things, we need to focus a lot of attention. And I know that part of the Cornell, what is it called? Cornell 2050 or Cornell 2030?
Cornell 2030
Okay.
project. And so those, when I had this figure, there's multiple ways to look at this. I mean, if you were to look at this on a per capita basis, it looked noticeably different considering the population in India and China. So that's something to for perspective. But that said, what is the number one thing that we could probably do as nutritionists in those countries? And we have this conversation, I would say, every week for the past 8 weeks easily, improving our understanding of feed chemistry on a global basis would probably be the best way. And for example, in India, there's certainly, I think, a high demand in like a country like India to better understand feed chemistry, to get high quality feed chemistry data, and then integrate that into like our CNCPS feed library, or any model of feed library, as a way to better predict nutrient requirements that are specific to that region based on the feeds. Because what else, the adaptability of the Northeast feeds for Punjab, India, is not very good. And I also think there's a breed component and there's an environmental component. I mean, God, in South Asia, the heat stress is a big deal. And there's not a lot of, you're dealing with indigenous cattle, you're dealing with buffalo, and, many would say ruminants are ruminants, but there are differences there.
Mm-hmm. I think, and if Lynn's interested in talking as well, that is one of the struggles that we run into when we're doing trainings in countries outside of the traditional European Northeast type feeds. we've been working with a man in India who has been trying to pull together some of those feeds typical of that area and get some good analyses on it. But yeah, I mean, that is very true, that our libraries don't work for them.
Yeah. I mean, we're trying to think about how to help in terms of visiting scholarship training opportunities, but a lot of that is led through the Cornell 2030 project and the Atkinson Center and various NGOs that are interested in this. So it'll be interesting to see how this evolves with time, but it definitely caught my attention in the last few months, and we'll see what happens.
Did Pete Van Soest do a bit of legwork on that? Wasn't he working in India some of the time?
Yeah, I mean, Vandenberg, Mike will tell some stories. But, I think most of my recent connections have been through with the help of Mike, but also just a lot of cold calls. I mean, India is very unique in that you have to have really government buy-in to have, I think, action. In that, you have to connect with the National Dairy Development Board or National Dairy Research Institute. I think it's in Cornell. But you have to have these right connections with the right people, I think, to really, and then have their commitment, right? And so it's going to take small steps, but initial indication is that they're interested in figuring out something to make this happen.
Yeah,
I think you're absolutely right, Joe. I think that's kind of spot on. You got to know the right people there to do anything.
Yeah.
Tom is actually heading off to Vietnam in 2 weeks, Lynn. And I think he's gonna, I think that we may gain some information there.
Yeah. I mean, the problem is, how do you connect, people in the United States? Like, I was not trained to solve this problem. And none of us in the United States would argue are. And so it takes a very unique kind of skill set and right connections, but we've got to figure that one out. And it's going to require multiple people from different backgrounds to just be all on the same page. You know how hard that is.
Yeah. Lynn and I talk about that daily. Paula, I'm hoping I've given you enough time to get some questions queued up and translated. Are you ready to go at it?
Yes, I'm ready.
Perfect.
Hello.
Okay. My first question is, can the use of tannins reduce methane emissions? And what about different tannin sources? For example, grape seed or wood?
Yeah, wood. I can say I don't actively study tannins, but tannins have been shown consistently to reduce methane. The issue with tannins is that too much tannins, and I don't know the feeding level, but too much can suppress appetite, drop dry matter intake, right? And compromise digestibility. Now you talked about grapes, that's grape pomace, like that's something that we would study here in the Finger Lakes, right? In the wine, we're in wine country right here. Mm-hmm. That has been explored in a single study that I'm familiar with, has been shown to effectively inhibit methane. But that's it's a great source where you've got a regional feedstuff that could have a great good impact on methane emissions regionally, and also get rid of a byproduct, which is what cows do greatly. So, yeah, I mean, I think there's not a lot of research on that. I think it's not something that's going to have broad adoptability across the world, obviously. But I'll also point out that these are weak inhibitors of methane. We're talking maybe 10%.
If I can add something to that, it seems as though in the model, if you have any more than 8 pounds of grape hummus, your dry matter intake is going to be really, really low. The predicted dry matter intake is going to be really low. The cows don't always say that, but in the model, that's how it shows.
I've never played around with that. I should. I'm a little curious now.
I had to troubleshoot a diet probably 8 years ago, and that ended up being what the problem was.
Yeah, cool.
So it's right around 8 pounds, right around there.
Yeah, I think I was, when I was doing one of the videos, I was actually trying to hit that sweet spot or unsweet spot where it did make that decrease. And I don't think I got up to 8 pounds, Lynn. So, Paula, go ahead.
Yes. Okay. Thank you. The second question is, do you think it is more important to manage manure or diets according to their impact in emissions?
Yeah, and diet. I mean, diet for sure. I think enteric emissions, I think, in terms of methane, are more of an issue than manure emissions when you look at total emissions. Now, there's a caveat to that. One, manure is the source of nitrous oxide, which is, I think it's the amount of nitrous oxide from manure is 40 times that comes from a cow breathing. All right, so, and I think whatever you do in the diet is going to have potential benefits on methane emissions in the manure. So if you had just one place to focus, you'd focus on reducing enteric methane emissions, and some studies have demonstrated also reductions in manure methane emissions sort of concurrently, but it's certainly a minority of studies. But yeah, you really have to study both, though. I mean, I hate to advocate for just one because we often ignore nitrous oxide emissions just simply because we're not measuring it, and I think it has people's attention now. So, yeah, I actually looked at that grape question. I found the paper. It was about a 10% reduction, and they were feeding about 5 kilos of grape pomace, which is not great reduction.
Okay, thank you very much.
Paula, Paul, keep going if you have more questions.
I have one more.
Okay.
Okay, as you mentioned, different places have to be treated differently. Which are the main management strategies we could start implementing to be more efficient and though more environmentally sustainable?
In what country?
South America, for example.
South America. Yeah, I don't, I think we have, as we continue to do what we're doing, but enhance, feed for requirements. Number one thing we could do is feed for requirements. And I think that's easier said than done sometimes. Like I said this morning, I'm not an economist, and the diets that I create sometimes I think, result in remarkable efficiencies. But if I were to feed that same diet, the economics wouldn't look so great. I think we have to overcome that in some way. I think in the United States, the number one thing I think we could do is just become more informed about these feed additives as they emerge. So I'm thinking about the next 10 years, and you have a farmer that's going to be approached to sort of say, hey, use this feed additive, use this feed ingredient, reduce methane, but enhance performance. Well, there's got to be better transparency of data between scientists and agribusiness and farmer, and we've got to better educate that performance is just likely the main driver of adoption, and that we need to be transparent about the efficacy in that methane mitigation. We often make sales pitches. I see these where product X reduces methane by X percent. Well, that's great, but what happened to nutrient digestibility? What happened to, nitrous oxide? What happened to, milk component production? I mean, we have to better educate using a holistic perspective to understand the true impact. Hopefully that helps.
It's complicated. And and I think that I'm recalling the paper that was I think it was just an exercise in what if that Robin Wright, is it Robin Wright?
Yeah.
And Mary Beth Hall did a few years ago.
Yeah.
It's complicated.
Because they did. Well, I don't know if this is the same paper you're talking about, but I always reference Robin's paper where she looks at the efficiency on the basis of nutrient supply. And so as we're thinking about, this is so complicated because we just talk about emissions based on unit of intake or unit of, energy corrected milk production. Okay, that's probably where we all talk about. But you could do this on the basis of individual nutrients.
Yeah.
Crazy.
So Paula has another question. I'm going to ask it because I want to, we did talk about that this morning a little bit. Do you think that, right now there's no incentive to try some of these things that maybe don't increase milk production, decrease emissions, but, either they decrease milk production or they keep it the same. There's no incentive for a farmer to use it other than he wants to save the planet. And we all think very short term. Do you think there'd be the opportunity for greater adoption if there were, that not the stick, but the carrot? Let's put how much.
Yep.
Let me get my mouth wrapped around this. Make our equations robust enough to be able to offer a prediction, much like we do with the work that has been done in nitrogen, phosphorus, and potassium emissions or excretions, much like that, where we have our CAFOs. Is it possible that might be something that's examined for emissions, at least speaking from a US standpoint, but globally, obviously, we need to address it.
I mean, I think I understand your question, but
I know.
I think we can do a better job of predicting emissions, especially in response to individual feed additives. I think we don't that total quantitative data is going to come shortly. We'd hope the next 5 years. But in terms of the adoption, I already know one milk processing plant that has started to encourage producers to use a certain feed additive. And in response, there was just so much confusion about what does this feed additive actually work and how's it going to affect repro and how's it going to affect, my fresh cow diseases. And, I think before we get ahead of ourselves, we have to have better science. And so if you are going to incentivize somebody to use something, they have the right information to say, yeah, I can make an educated decision. In the case that I'm thinking of, there was not the adequate information for the producers to make an informed decision. And we've got to step up and accelerate some of the research here, and it's happening. I'm optimistic here, but it's going to be important.
Mm-hmm. Paula, coming back to you.
Yes, I'm here. Okay. You told us something about the alga, but do you have some experience with the use of Mutral to reduce methane emissions?
No, I have had conversations with the Mutral folks. Again, I put that in the plant-based extracts. I don't want to disappoint the Mutral people, but I'll say that we really need solutions that inhibit methane beyond 30% and enhance performance. I think products like Mutral have a position in the marketplace, but when combined with other approaches that really optimize the inhibitory efficacy, Mutral alone is not going to solve the real problem here, but it can be part of the solution.
Okay, thank you.
Okay, any more, Paula?
No, by now.
Joe, is the work that you'll be able to do with the chambers going to work towards making sure that the emissions equations in CNCPS are robust as possible?
Oh yeah, for sure. We've got to be very busy here.
Yeah.
We're trying to figure out, there's been such high demand and interest, and we're really trying to position ourselves to handle the incoming flux of trials. And yes, this is absolutely on our mind. It's not just CNCPS, but Dr. Reed works with Rufus and how we can integrate the data into that. I'm not going to get ahead of myself, but there's also going to be other data-driven projects in the works that you'll soon hear about, I'm sure, in the next few weeks. But yeah, how do we better process the data? We want the data not just to be benefit to us either. I mean, there's a goal here to share the data so other models can be improved as well. Because we realize that chamber data, like chambers aren't the only tool here in the shed, but they're not. Chambers provide a very unique part of the data that's missing, and they're not everywhere. And so we got to really share the data to accelerate the refinement of models like yours.
Have you done any comparisons with do you know the source and the robustness of the emissions equations in the NASEM, the new NASEM model?
No,
Okay.
In time, I'm sure.
Yeah. I'm gonna let Paula, she's got more questions about Mutral.
Yes, a follow-up question. What would you use to combine with Mutral to get that 30% you would like to have?
Yeah, so I know you're asking, you want an answer to a question that does not yet have an answer. But if I had to hypothesize, I envision Mutral in a way acts like a rumen modifier. It's a way to alter the rumen microbiome, methanogen populations. It's not a direct inhibitor, right? And so in that particular case, I think when you would co-supplement with a direct inhibitor, something like 3-NOP, which is obviously not in the US, but 3-NOP and Mutral, can you get sort of a synergy? You have to have a mode of action that is complementary to each other. And so rumen modifiers like plant extracts, direct inhibitors, and changing sort of propionate supply, I would argue are three very unique modes of action. You could throw fatty acids in there too in the biohydrogenation sink, but direct inhibitors versus rumen modifiers, I think that's where you're going to see a lot of benefit. And you see that in the one slide looking at 3-NOP in oil. Like that's a direct inhibitor and a rumen modifier, and you get a synergistic response. Now, I would love, this is the issue, and to all the companies in the world that support this kind of research, we really need those kinds of studies. And I would argue feed additives versus and their interactions with base feed ingredients is really where we should start. And that's not going to create any conflict in terms of sponsored research agreements.
Okay.
Thanks.
Thank you, Paula. Unless I have any more questions from anyone, and any of my co-hosts have anything more to ask, I am going to say, Joe, you probably have the abandoned wife that's holding dinner for you.
Yeah, well, they went to the park without me. Enjoy the music, but that's okay. I'm getting ready to move out of my house, so I have a lot of packing to do tonight.
You said that when I bugged you for your presentation. Yes. I felt so bad.
Yeah, no worries. Okay, thank you.
I think Marcos has a question.
Hi, hey Marian. Hi Joe. I have a question here. Can you comment a little bit more on seaweed? Like it's so toxic. Like what triggers that? Like, do you see any future or what kinds? Or get a little bit more. I found that very interesting.
All right, so I'll just give you my speech on seaweed. And so seaweed is I didn't hear the first part of your question, but the seaweed is a potent inhibitor. I think there is a lot of emphasis on focusing on dose, feeding dose. I think the initial studies were likely overfeeding seaweed, and that's where you start to get some of the toxicity effects on the rumen epithelium. I know I've been talking to some people. There's an Ocean Research Institute in Maine, and then I've been talking to some folks at New Hampshire too occasionally, that the goal there is to dial down the feeding dose so you don't get the toxicity effects. But even at some of the lower feeding levels, you still see the active bromoform ingredient in milk. You don't see it in meat. It does not, it has consistently not shown up in meat, but you do see it in milk. It is detectable, is responsive to dose. And, you know, it may not, it's below at least the EPA's sort of toxicity limits, which is a good thing. But in something like that, it has profound efficacy, we have to be careful. Just I'm trying to educate the consumer along the way. I mean, they think seaweed, it sounds healthy. I'm going to turn into a really healthy person when I eat it, and I drink the milk that cows eat it. Well, bromoform, when the consumer finds that out 5 years down the road, oh, bromoform in my milk, I don't want it. That's an issue. We have to prevent that before we're too far ahead. The other thing is there's very little research on the effects of toxic heavy metals in seaweed. And now I've talked to a variety of people across the world, and the one thing that I've learned is that the source of the seaweed, it could be the same species, but where it was harvested can have marked differences in the trace in the heavy metal content. And that's not well documented, and we don't know what effect it has on the animal or in the milk. You also have to think with seaweed, the concerns there is that, yeah, you could farm it from, harvest it from the ocean. How does that affect the ocean's ecosystem? You have to think about, you're going to cultivate it, how are you going to process it, dry it, there's more energy there, how are you going to ship it? Those things we have, that's a great example of where that life cycle assessment is needed. Very, very hopeful, but a lot of questions.
Joe, would those bromoforms, you said they're below a toxic level in the milk, but what if that milk was used to make cheese?
Oh, yeah. I don't that's a good question. I don't know how that would change at all, but my guess is that it's still, I can't answer that question.
No, it just occurred to me when you said it's diluted enough in the milk, but does it get concentrated when you have a cheese that you have a 10% yield per gallon?
I don't know how you're not going to I think one of the immediate issues, let's say everything was really safe and ready to go. There's no way right now to sort of produce that in a large enough scale. That's a big issue.
Joe, do you know of any experiment that saw a reduction in methane with seaweed, but like with no depression in cow performance or dry matter intake, like same performance and lower methane at a low dosage?
Yeah,
do you know any?
I can just say that I haven't looked at probably every study, but consistently you see the drops in intake. Milk production probably doesn't change. But you do see maybe perhaps a small increase in efficiency or just no change, but that drop in voluntary feed intake, now granted, the studies that I'm looking at are probably the higher dose studies. I know there's more studies in the pipeline looking at lower feeding levels, and we will see. But right now, current evidence says it's dropping intake.
Okay, thanks a lot.
Yeah.
Go, Marian.
Thank you, Marcos. I think that wasn't Frank Mittler's lab working in that at the Clear Center?
Yeah, Ermias is too at UC Davis. I mean, they're the pioneers in all of this. But I'd love to see some seaweed respiration chamber experiments out there.
Okay. If I don't get any more questions and none of my co-hosts have any questions, I am truly going to let you go this time.
All right, perfect. Thank you.
All right. Thank you, everybody, for joining us. And thank you so much, Joe. It was delightful. All right. Bye, everybody.
Bye. Bye-bye. Bye, everybody.
Bye.
Bye-bye.